Good morning. I'm very pleased to be giving the lead-off presentation for this year's Microelectronic Engineering Conference. I'm Karl Hirschman, Micron Professor of Microelectronic Engineering, and I will be discussing design considerations and system integration of backplane thin film transistors for micro-LED display. The following is an outline of my presentation where I will be giving an introduction to micro-LED displays, discuss active matrix thin film transistors as the backplane, which is used in pixel addressing. We'll review the pixel devices and circuits, device models in simulation that was used for this work, and most importantly, the heterogeneous integration of micro-LEDs with thin film transistors. I will wrap up at the end with devices and prototypes that are in progress. The following diagrams show the two primary technologies used in today's flat panel display products. On the left side, we've got liquid crystal displays, which have a backlight that shines light through the individual pixels, and you've got a liquid crystal which acts as a filter, and it will either block light or let a significant amount of light through, depending on the voltage that is set by the thin film transistor that controls the transfer of data onto the pixel. On the right side, we have organic light emitting devices for OLED displays, and in this technology you have a thin film transistor backplane which is controlling the current flow through the light emitting devices by assigning a voltage to a driver transistor. And these OLED devices are really brilliant. The displays are quite amazing, and they have very high resolution displays. Being an emissive display, you have an advantage in higher contrast over the liquid crystal display. There have been significant advances in both of these displays as far as the color and stability and the resolution, of course. The cost of these displays continues to come down. One of the big challenges in these displays, though, is the difficulty in seeing them with a bright ambient lighting, for instance, in bright sunlight. This picture shows a guy who is struggling to see his phone with a high ambient lighting, being outside in bright sunlight. And to make matters worse, he has sunglasses on. So this image is going to be very difficult to see, even with the best cell phones, because the emission, the image is just not that bright. An advantage in micro LEDs is that they can be terrifically bright. In fact, they can be blinding, where they actually would cause discomfort if you look at them too long. Micro LEDs have a distinct advantage in brightness over either LCD or OLED. This picture shows a micro LED display that was demonstrated by Samsung at the 2018 Consumer Electronics Showcase, a 146-inch micro LED TV called The Wall. Perhaps not practical, but at least Samsung beat the competition, so they have bragging rights on that. LG was actually not too far behind, and they had to outdo them with a 173-inch micro LED TV at a European electronics showcase in 2018. So these really large micro LED TVs are really just for demonstration. They would be much too expensive for a typical consumer to buy, but they are extremely bright, and the colors are amazing. So they really demonstrate a wonderful display technology. Perhaps not practical, though, for these applications. Micro LED displays certainly have a place where you do need a bright image with background ambient lighting, such as in automotive displays, outdoor signage, and other niche applications. So the micro LED advantages are fine resolution in comparison to, of course, standard LEDs are millimeter scale. Micro LEDs are down at the micron scale, so they do offer a fine resolution that would be comparable to OLED, high brightness and contrast, and also very energy efficient light emitters. So that helps keep the power consumption down on the display devices. LCD is not that energy efficient. It's a filtering effect. To get that bright light, you have to expend a significant amount of energy for the backlight. Now, on the right here, this shows micro LEDs that are illuminated, just showing them lit up where you can't see the anything beneath. But these are 3-color, which would typically not be made on the same substrate. So these are likely transferred onto a backplane and are just uniformly illuminated. These are at micron scale, so these devices can be tens of microns in size, down to even smaller than that. The manufacturing challenge is to integrate these micro LEDs, which are fabricated on compound semiconductor wafers, onto the thin film transistor backplane, right? The transistors that are going to control the pixel addressing and emission of these devices. And these displays, regardless of the size, you're still going to want high resolution, and there will be millions of devices involved in transfer from one substrate to another to populate the arrays. So, for instance, a 4K display today, high-density display, would have 3840 by 2160 pixels, and you've got at least 3, maybe 4, sometimes they double the blue, LEDs per pixel. So with full color, you've got at least 25 million devices for a 4K display. Probably not well suited for large panel manufacturing or transfer of devices onto large panels. That would just not be a suitable manufacturing technology. What some display companies are pursuing is more of a modular concept, which is illustrated here, where you would have optimally sized display modules. So here, as you can see, we've got 9 modules that are arrayed with very close proximity. These would operate in parallel to present a large continuous image. And for this to work, however, it would need seamless transitions between modules for a high-resolution display. You cannot skip a row or a column and expect people to not see that, right? So this technology certainly is of interest in order to be able to populate the modules with micro LEDs at a scale that would be manufacturable. The challenge then is to have these line up with very high precision, with very little space, so you do not miss a pixel. Corning Incorporated is pursuing a technique that can enable such a modular concept. And what they have been developing are wraparound electrodes for micro LED tiled displays. This is a paper that they presented at the Society for Information Display Week last summer. And I'm working with Corning now in proof of concept in enabling this technique. So what it involves is essentially routing contacts around the edge of these modules from the top side, where you've got your thin film transistor backplane and micro LEDs, to the back, where the back electrodes can then interface with a printed circuit board for control circuitry, etc. So you've got your IC driver board on the back, and you've got the micro LEDs and thin film transistor displays on the front, right? This would be a top surface emitting display where the LEDs are are emitting upward rather than down through the glass substrate. So the challenge for this is to be able to route these interconnects and need very, very little space, of course, because you're going to need to put another one of these modules right up against it. And these electrodes may be fragile, so they would need also to be protected from damage and things like that. So, but if this can be achieved, then and these modules placed with high precision, then it would have some advantages in other approaches. This just shows an enlarged cross-sectional view of two modules that are adjacent to each other with the wraparound electrodes coming around the edges here, and there's some overcoat material to protect that. And notice that marked here is the pixel pitch, where there's essentially no room for some extra space in between these things. Any disruption of that periodic arrangement of pixels is going to be easily seen by the observer, and that also means that at the edges the real estate allowance here has to be very small, because everything in the pixel is already being made as small as possible. So there are some significant challenges to this, yet this could be an enabling technology for micro-LED modules. So for proof of concept of this technology, Corning approached RIT and basically said, let's make a micro-LED display. There was already some collaboration with Tyndale National Laboratory in Cork, Ireland for micro-LED fabrication and micro-transfer of micro-LEDs for hybrid integration. So RIT's role in this next phase of the project, this was the active matrix portion, where we're responsible for the TFT backplane design and fabrication, and also system integration as things get put together for the eventual control of the display. Corning Incorporated, of course, they're the project sponsor, and they are doing what they are good at in developing their technology, glass cutting and specific attention to the edge chamfer, so the electrodes can easily go around the edges, and actual fabrication of the wraparound electrodes themselves. Now the following block diagram just shows a general schematic for an active matrix system, where you've got your system controller, right, which would control the data to the column shift register, which eventually then provides all of the image information. So that is information that the TFTs transfer to the drivers, which eventually then light up the micro-LEDs. The row shift register is basically a counter. It's shown here receiving data, but basically the role of this is just a count down through the rows. So you've got a certain row scan frequency, and the signal, the roll pulse just continues to go down from the top to the bottom over and over and over again. So many cycles per second in order to provide a complete refreshed image on the display. And then of course we've got the display backplane. So this is the array of thin film transistors that do that active matrix control addressing. You've got passive information and storage of information that allow these devices to continue to emit throughout the entire cycle of the row scan. So we'll get a little bit more details as to how this all works together. The active matrix backplane layout arrangement, or a portion of it, is shown here in this black and white rendering. We've got a couple thin film transistors and a micro LED here, along with a storage capacitor. So I'll be focusing on these details, just highlighting one pixel in color on the lower right. So let's take an additional look at what's inside this pixel. So here we've got the layout, and on the left is the circuit schematic. So this is commonly referred to as a 2T 1C active matrix pixel. So we've got two transistors, a pass gate thin film transistor and a driver thin film transistor. And also in parallel with the driver gate, we've got this storage capacitor, which will allow charge to be stored to help suppress charge leakage, and it will also help mitigate voltage losses that occur due to charge sharing, which we'll be talking about some of those details. And we've got our micro LEDs, so the driver transistor is controlling the amount of current flow. This operates as a current source to provide a constant amount of current going through the micro LED. The grayscale and brightness control of the pixels can be done a couple of different ways. One method would be a current modulated brightness, where a digital to analog converter would be used to take binary data and transform it into an analog voltage on the column line, and the row enable will then pass that specific voltage over. So a lower voltage, of course, would offer less current. A higher voltage would be more current. So the more bits you had in the DAC, the more levels you would have in brightness, and a higher voltage equals brighter micro LED. The row enables the column voltage to reach the driver TFT, and data is stored on that storage capacitor until the next row enable, which would be the reciprocal of the scan frequency. The other approach for brightness control is a pulse modulated brightness. In this case, the column signal is digital. It's either a 1 or a 0, and the row enable will allow the column data to reach the driver TFT, and it's stored on the storage capacitor. So far this is similar as the previous strategy, except in this case there's not a variation in voltage on the driver. It's just a 1 or a 0, right, high or low value, and brightness is controlled by the percentage of time that the pixel is on rather than the brightness of the micro LED based on the amount of current. So the eye integrates the brightness over time, and then that gives the observer a perception of brightness that is basically the same as the light either emitting a lot or emitting only a little bit. So the number of levels then of grayscale is based on that scan frequency, because now you have to break down each level of brightness into a certain number of bits. So a fine grayscale or high color depth and a high perceived refresh rate demands a high scan frequency. This table shows timing requirements that are needed in order to ensure that the signals are properly transferred in the time allowed for the row enable, depending on the number of rows and the brightness levels, the number of bits used to encode the brightness or levels of brightness. I've got the first row here for a 1080 high def display with 8-bit grayscale or 24-bit color. So each color has 256 levels of brightness that it can be. And if that is used in a pulse modulated grayscale with a perceived refresh rate of 60 Hertz, you multiply the brightness levels by the perceived refresh rate, and that gives you the scan frequency, or 15.36 kilohertz. So the row enable time then is the reciprocal of that scan frequency divided by the number of rows that you have. So for this high def image with pulse modulated grayscale, the row enable time works out to be 60 nanoseconds, which is clearly not going to be satisfied by our thin film transistor technology. We could use a silicon wafer and make a fairly high performance CMOS circuit that would do the job nicely. And one might ask the question, why not fabricate these modules on silicon? And you certainly could, but that would not enjoy the benefit of large panel manufacturing where the backplane can still be made, these modules can still be made on extremely large panels of glass and then cut up into modules. So the economy of scale, you wouldn't want to use 300 millimeter silicon wafers for display. It would be too costly, and with the infrastructure of flat panel manufacturing, glass would be a more appropriate substrate. So that means that we need to do this with thin film transistors that are not going to be operating with time on the transition times on the order of nanoseconds. They're a little bit slower than that, and I'll be describing those too. Now, for these other row options, we've got 380 rows and 50 rows, and these are for the prototype devices that we're making. And I've got a breakdown here with different bits of grayscale, perceived refresh, and the corresponding scan frequency and the row enable times. And you can see that as I'm going down the rows, we're getting more conservative where our row enable times are increasing. But these are times that we have to keep in mind to make sure that when we do our simulations of our pixels and RC delay and things like that, that we can keep up with the times that the period in simulation ends up being below the maximum time allowed for the row enable. Our thin film transistors are made from amorphous indium gallium zinc oxide, which is a sputter deposited material that has a significantly higher channel mobility than amorphous silicon, channel mobility of around 10 centimeters squared per volt second. We've been working on this material in collaboration with Corning actually for a number of years. And this material now is become widely used in display devices today, so it is in manufacturing. We have modeled both the on-state and off-state characteristics of our TFTs. This shows representative characteristics of a TFT channel length 4 micron, width of 24 micron, and it shows measured characteristics overlaid with modeled characteristics. We've got some references below where original work was done with some of my former students. Actually, Eli Powell is one of my current students now. He's back again. And that was the work on the on-state representation. And Hector Rivera, who now works with Dr. Preble's group, he actually did this with it for his master's project in extending the model to the off-state. So this allows us then to use these compact models of the device operation for our circuit simulation. We also have developed a compact model for the MicroLED. It's just purely empirical. It can be modeled by a non-ideal PN junction diode where we have an exponential region and then a polynomial fit for this upper part of the characteristic. Unfortunately, it's just not that well modeled by the addition of series resistance and shunt conductance, so we just went with an empirical approach for that. This, by the way, is a blue LED characteristic provided by Tyndale that we matched up. This shows the pixel circuit. Now, in this case, in order to get an accurate simulation of our pixel transient and things, we need to include the parasitic capacitances that are involved, the overlaps with the gate, source drain regions, etc. So you'll see these various elements have been added to the circuit in order to properly account for those. I also have a cross-sectional schematic of our thin film transistor, which also shows the metal overlap regions of the source drain and the gate electrode, and those correspond to those additional elements there. So the circuit becomes more complex, however, the simulator can readily handle those additional elements. So we've done circuit simulations for the MicroLED and driver current matching, pixel transient response, Rowline RC delay, and also voltage losses, just IR loss effects on the VDD and ground lines. The following shows MicroLED and driver current matching, where we have our driver TFT output characteristics and an overlay of the load characteristics of the MicroLED. And we've got a couple operating points here identified which verify that our TFT will serve as an appropriate current source, focusing on a range between 20 and 50 microamps based on the current voltage characteristics of the MicroLED and the emission characteristics. The following shows results of pixel transient simulations at different storage capacitance values in order to investigate the trade-off between the delay time and charge redistribution, which can cause voltage losses when the row signal returns back to a low. One note is that the TFT gate overlap capacitance is around 0.23 picofarad, so a storage capacitor of 1 picofarad is 4 times that of the overlap capacitance, so that just kind of provides a reference for comparison. The Rowline RC delay was also simulated as a distributed RC network, and basically looking at the rise and fall waveforms with the estimated line resistances per pixel, as well as the parasitic capacitances. And here I've got highlighted the results for the 380 monochrome. So this would be the columns here, right? Versus the 380 times 3, which would be the red, green, blue. Same number of rows, but the row RC delay is just going to be a function of columns. The more resistance and capacitance, of course, it takes longer for that worst case delay, which is shown by these waveforms. This slide shows a summary of the circuit simulation results. We've got some quantitative details on the pixel transient and row column RC delay, their contributions, which has to be considered in meeting the timing requirements. We also simulated IR loss and its contribution to variation in the current over the 380 by 380 display. In summary here, the lower operating current has a relatively low pixel delay and low IR loss variation. So the 20 microamp is certainly better suited for our design. The parasitic R's and C's are adequate for a 50 by 50 monochrome prototype and RGB. However, in order to satisfy the timing requirements for the 380 by 380 with the desired grayscale and refresh, some improvement needs to be done. And both pixel and interconnect modifications are required to scale up the 380 by 380 red, green, blue. This shows a new design for our red, green, blue pixel. So not only does this accommodate all 3 LEDs and 6 transistors, right? It also addresses a lot of those needed improvements that I just mentioned. It offers a relatively compact design, efficient use of real estate. It took a long time, a lot of iterations, and a few students have been working on this. It keeps line resistances and capacitances to a minimal, and the edge pixels facilitate connection to the top level metal, which is preferred arrangement for the wraparound interconnect. This design also presents a convenient arrangement of MicroLEDs for transfer hybrid integration. As you can see, the MicroLED locations, they're all in the same general area, and they're all in the same orientation. For micro-LED integration, what I've got here is a cross-sectional view showing the driver TFT and the storage capacitor over on the left, and the processes then that we use to go from the TFT backplane up to the micro LED. So we've got a third layer of metal which serves as an interconnect, and then we apply what's referred to as intervia, which is a PDMS material that is photosensitive. So this allows us to actually pattern it and develop it, and then it's cured, and this is the material that the elastomer stamp is used to place the micro LEDs on top of, and then they stay on this intervia. So the micro LED is placed, and then a metal 4 interconnect layer, which is very thick to accommodate the step coverage over the edge of the micro LED, that's then applied as a final interconnect. And as I mentioned, our new pixel design uses this layer of metal as the interconnect to the wraparound electrode. The transfer printing is done by technology developed by a company called Acceloprint, and they actually have operations in Ireland, and there's a couple of these systems at the Tyndale National Laboratory over there. This shows a view of representation of this elastomer stamp, which goes into contact with a native wafer for source devices, lifts them up, and then can be used to place devices onto a non-native substrate. I actually have a video clip queued up that I'll switch to just to show this this video, so you can see how this process works. Elastomer stamp, touch, alignment, and place. Another layer of devices, different stamp because a different arrangement of source devices, and metallization done following that to device transfer. So for our micro LEDs, we've got an actual SEM image of micro LEDs fabricated at Tyndale, and the micro LEDs are made from indium gallium nitride, the blue and green, and aluminum indium gallium phosphide for red. So they're actually made on two different substrate wafers. And these are released, but they're tethered, so they have these anchors that still hold them in place. So the elastomer stamp lowers down and comes into contact, lifts them up, breaks them off the tether, and transfers them onto the backplane, onto that intervia PDMS material. It's interesting, the elastomer stamp and the intervia are almost the same chemical composition, yet the stamp can pick up a device and move it over and transfer it and release it and let it go on the intervia material. I've just got another slide to kind of quickly run through that sequence where we've got devices that are released, meaning that there's nothing under them, but they are anchored, ready for transfer. The stamp has a post so it can pick up individual devices every so often. So there's many more higher density of micro LEDs on the source wafer than there will be when placed on the target. So this device that's right underneath this region here, that is going to be picked up, and a rapid pickup after being in contact will break the tether and then allow it to transfer. So it's on the elastomer stamp at this point, and then it's placed onto a target substrate surface, which is the intervia, and this is a different substrate. It's not our TFT backplane. And then the stamp is detached with a slow release using some translational shear. And you can see kind of a twisting here where it peels off, and then that micro LED will stay there, and then the inner via is cured at about 200 degrees C, and it is a permanent part of that structure then. So it's as if it was always made there. Not quite like monolithic, but pretty close. And then you do metallization to do the interconnect, and this shows an integrated TFT micro LED pixel. This is our pixel design, and our pass gate, our driver, and the micro LED is placed, and metal interconnect to wire things up. Okay, we've got some actual devices on glass, some arrays in progress now in fabrication. The one on the left is a microarray test structure. It's a wired 3x3 die arrangement of some test die with relatively small arrays. You can see this one actually got cracked, but we have others. And on the right, this shows at glass wafer scale a small 1x1 centimeter. That's a 50x50 pixel design that is in the early stages of fabrication. But we actually, at this point, even have backside metal already defined for the wraparound electrodes, and this is at the point of the top side gate metal for the row and TFT gates. And this just shows from a design standpoint, an overlay of the 1x1 centimeter display, 50x50, with the printed circuit board interface, where the wraparound electrodes are going to be used to go from the front side metal to the back side metal. Of course, there's all of the wiring on the front that's going to bring the electrodes to the edge. The substrate will be aligned and bonded to the printed circuit board, and that's using an anisotropic conductive adhesive. It's somewhat non-traditional. We're investigating this new technology that may be available for this. We're hoping that works out. And then the printed circuit board would be populated with shift registers and interface with a field programmable gate array FPGA controller that controls the clocking, the data, and all of those things. So I know I went a little over time. I appreciate the organizers for cutting me some slack, and I want to acknowledge the following folks, my students that have worked in my research group specifically on this project, including a couple of undergraduate researchers, SMFL staff, folks at Corning, Sean Gardner, Dean Thalen, and Robert Manley, former PhD student here at RIT, and the folks at Tyndale Labs, Ji Lee, and Brian Corbet. Thank you for your attention, and enjoy the rest of the conference.